One of the amazing ideas to emerge from Einstein's theory of general relativity was the possibility of gravitational waves rippling their way across the cosmos. It took a century to verify this prediction. Their existence was finally confirmed by LIGO, the Laser Interferometer Gravitational Wave Observatory, in September 2015. What's in a name? LIGO has so far detected 3 gravitational wave signals, all of which are due to black hole mergers in the distant universe. The image below shows an artist's impression of the system that produced the third of these signals, detected on 4 January 2017. The black holes were 32 and 19 times the mass of the Sun, and were spinning in different planes, as depicted in the illustration which shows them just before their merger. The signal has been named GW170104. Guess why artist's impression of a close binary black hole item based on GW170104. Credit LIGO, Caltech, Sonoma State, Aurora Simone. Lovely Lisa. The detection of gravitational waves by LIGO was an incredible technological achievement. The European Space Agency (ESA) is planning to go one better by putting a gravitational wave detector in space, scheduled for launch in 2034 as part of ESA's Cosmic Vision program. It is known as LISA, Laser Interferometer Space Antenna. There will be 3 spacecraft orbiting the Sun in a triangular formation, consisting of a mother and 2 daughter craft, each separated by a distance of 2.5 million kilometers. They will form a precision interferometer with lasers monitoring the distances between the mother and daughter craft. A passing gravitational wave will change these distances very slightly, and this will be detected by the interferometer, paving the way for LISA. The LISA Pathfinder mission was launched in December 2015 as a stepping stone to the LISA mission. It was devised to test the technology that will be used in LISA and demonstrate the feasibility of constructing an interferometer in space. The goal was to show that test masses can be shielded from any stray internal and external forces and maintained in a state of almost perfect freefall. Remarkably, the spacecraft avoids any contact with the test masses contained within its structure by sensing their motion and adjusting its own position using microthrusters to compensate. This is essential if the sensitivity of the interferometer is not to be destroyed by inevitable perturbations that the spacecraft will suffer. These arise from a number of sources, including stray gas molecules within the craft, the solar wind, and micrometeoroid impacts. ESA announced in June this year that the technology trialed by LISA Pathfinder has performed beyond expectations, which means it will certainly be sensitive enough to detect gravitational waves when deployed by the LISA mission. What will we see? LISA will greatly enhance our ability to study gravitational waves. It will detect signals invisible to LIGO and other ground-based gravitational wave detectors, as it will be sensitive to gravitational waves with much longer wavelengths that are produced by much larger systems. Although the black holes that merged during the GW170104 event were very massive, they were only 190 and 115 kilometers in diameter, with a merged black hole around 280 kilometers in diameter. These are very small objects by cosmic standards. LISA will detect gravitational wave signals emanating from tightly bound binary systems containing 2 compact objects that may be white dwarfs, neutron stars, or black holes orbiting each other prior to their merger. For instance, a binary black hole system such as GW170104 would be detected weeks or even months before the merger event. This will enable the position of the binary system to be located in the sky and the time of merger to be accurately predicted, which will greatly aid in visual identification of the merger event. Supermassive black holes. There is a supermassive black hole of 4 million solar masses at the center of our galaxy. Most, if not all, galaxies are thought to harbor a monster such as this within their core. LISA will be able to detect these beasts devouring nearby stars. It will also detect mergers of supermassive black holes. Such extremely violent and spectacular events must occasionally happen somewhere in the universe. We can look forward to finding out much more about them. The creation and early growth of supermassive black holes is still not well understood. LISA should detect their birth pangs and provide important clues to how they formed and their relationship to quasars in the early universe. LISA will also help to improve models of the immediate aftermath of the Big Bang and the very early universe. As an important bonus, LISA will add to our knowledge of fundamental physics by providing stringent new tests for general relativity. A version of this post originally appeared on Quantum Waves Publishing. Featured image credit Astronomy by Pexels. Public domain via Pixabay.